right, thank you very much, Frank, for this kind invitation and for your kind introduction words. In this talk, it's a short talk, I'd like to give you a sort of sampling of a few experiments we've been doing in the past, let's say, 10 years with single gold nanoparticles in the view of doing things with single molecules. So this is the current composition of my group. Let me see this, if this, yes, it works. So this is not a laser pointer, but it's a software pointer. It's also, first time I use it, usually it's very difficult with a mouse to have this, but it's working reasonably well if I'm not moving too fast. Yeah. So this is the current composition of the group, but of course the work has been done in the previous years, and of course I would mention the people who contributed to this work in the past. All right, and this, as said, was done at Leiden University at the Institute of Physics. All right, so this is a brief outline of the talk. I will give an introduction on gold nanorods very briefly. I think most of you know about plasmons. I will not insist too much. I'll give a very short primer on sensing. There is a big gap between a sensing experiment in which you detect something and a sensor, which is really an element which has to work in under very adverse conditions in industry or elsewhere. And there is a very huge gap between the principal demonstration, even with a molecule, a single molecule, and an application where you really want to use sensors for useful things. But so I'm really at the fundamental side. I will not go in the direction of real sensors. Now I will show you some things you can do with just Plasmonic. Let's say Plasmon itself. Fluorescence enhancement, that's the fluorescence of a single molecule can be enhanced by Plasmonic effects. I will show the example of methylene blue. And a more recent experiment with two-photon excitation, which may be an advantage. If time allows, we mentioned briefly recent experiments on nano bubbles. Right, so this is to just set the stage for the experiments. So we are doing optical experiments, and basically it looks very much most of the time like a fluorescence experiment in which we have an excitation laser, so this yellow beam here, which we focus with some suitable optics on our sample, usually on a confocal point. You can also do wide field excitation, but usually it's confocal. And from this point, we collect optical signals, most often in the backward scattered, backward emitted geometry, whereby you can use the same optics for both excitation and collection. That's very convenient. Of course, nothing prevents you from using two different optics at the cost, of course, of more difficult adjustments and more complicated, more complex setups. Well, for fluorescence, it's very easy. You just filter with suitable spectral filters to get rid of the excitation and take the photons, single photons that are emitted by the object. And this is basically what we do with gold nanoparticles for photoluminescence and in many cases for non-linear optical signals. So I will give you some examples in the following. Right, so this is a typical image of single molecules acquired in a confocal mode. So what we do is scan our laser, excitation laser, raster scan across the sample. Yes, here it is. So this is my laser, so I need some training to have the proper scanning. So this is the way it goes with a raster scan. And whenever the laser spot, diffraction limited spot, hits a molecule, an emitter, a molecule in this case, we get a fluorescent signal. And we plot this fluorescent signal in this image as a function of position. And this gives you an image where you see single molecules. Right, single molecules in this case, the molecules are blinking. I will not discuss this now. Okay, so now let's go to gold nanoparticles. Also very shortly, I think most of you are familiar with this. They are metallic. Gold is convenient for this application because it's a very inert metal, doesn't react very readily with oxygen or water. So it's chemically reasonably stable, inert. And therefore, the electrons are, the metallic properties are very well conserved. They do not depend very much on the conditions in which you look at them. And when you excite these particles optically, you apply a variable electric field, an AC electric field that moves the electrons back and forth with respect to the heavy ions. And this translates into a very large dipole moment, which will interact very strongly with the light. And this will give rise to scattering, but also give rise to a large surface density of charges. and who says surface density of charges says electric fields. So there will be large electric fields in the vicinity of the surface of the nanoparticle due to these surface charges. If in addition to this metallic property you play on the geometry of the sample of the particle by taking an elongated particle as a nanorod here, which I sketch as an ellipsoid, the surface density is even larger. You see that the number of charges per unit area is even larger in the case of a rod than in the case of a sphere, which means that this surface electric field will be even larger. And in this, you can take benefit of to enhance interactions with objects and to use sensing properties. So in many applications of this plasmon, it's a very simple and powerful analogy to reason on these moving electrons with a harmonic oscillator picture in which a mass, which is the electron mass or the effective mass of the electrons, is shaken, is attached by a spring. The spring is due to the Coulomb forces between the plus and minus charges. So this, of course, if the charge is small, the force is small. And the more you displace the charges, the larger the force. So this behaves like a spring. So you have a spring mass system that resonates. So you have the resonance frequency, that's the plasmon resonance, which in the case of gold happens to occur in the visible. For gold, spherical gold nanoparticles is about in a green at 500 nanometers or 530, slightly size dependent. Whereas if you move towards elongated particles like rods, you can shift these transitions all the way down to the near infrared, 1 micron, even longer if you take gold nanowires, which have extremely large aspect ratio, very long dimensions. All right. Okay, so these gold nanoparticles, gold nanorods and nanospheres, are usually in our group nowadays commercially available, but we also make them. And you make them by chemical synthesis from solution, which leads to extremely high quality crystallographic quality. So you see here TM images measured in Australia, by the way, by Peter Zeisler many years ago, where you really see that it's a single crystal. You can, if you are sitting in the front, you see that it's even possible to see the lattice planes of the lattice of gold, which really means that it's a single crystal. And it means that they have excellent conducting properties, even at visible, in the visible range. And that means that you have the nicest possible resonance that you can have with gold, in principle, in these nanoparticles. I should stress that this is not always the case for the sputtered or nanofabricated gold particles, because they are polycrystalline, they have many grain boundaries defects, which makes that the conducting properties are not as good. So by using chemistry, you can really have a much nicer crystallographic quality than using physics in this case. You would expect usually the opposite, but in this case, it's not what happens. All right, and this translates into a very nice and very narrow sharp resonance. So this, you see here a few examples of nanorods that we imaged either optically here or within the SEM by electron microscopy. And you can go on each of these particles. We can make sure in this way that this is a single particle because we have the image. And we can look at the resonance, and you see it's a nice Lorentzian shape with a given width. And of course, because this particle is slightly different, the position of the resonance is slightly shifted according to the aspect ratio of the particle. Okay, so why do we like gold nanorods so much? It's not that the enhancement of the field is larger with this particle. It's rather modest, actually, as a matter of fact. But there are specific advantages that we like. First of all, the surface plasmon resonance is narrow, intense, and tunable. So that's, of course, the main advantage of the rods. By changing aspect ratio, you move the plasmon. You can, in a sample where you have many different gold nanorods, you can choose the ones which have the plasmon exactly the right frequency that you need, that you desire, that you need. And they are controlled and reliable. As you saw from the image, all these particles really have very similar shapes. Of course, the length and diameter vary slightly, but they are all cylindrical with more or less hemispherical ends, capping ends. And that means that they all more or less behave the same way, of course, with different plasmon resonances, but the local field, the properties, all resemble each other very much. So you have a sort of calibrated response. This is not the case if we make much more complicated particles made of two particles, for example, because then the gap and the respective orientation of these two particles have a very strong influence on the plasmonic properties. This is not the case for rods. It's much simpler. It's possible to functionalize them. Deep functionalization, that's a property of gold, very nice properties. It's possible to do thiolate bonds that allow you to covalently bind all kinds of molecules to the surface. And what is very important in many cases is that the structure of a gold nanorods is very open. It's just a bar with an end, and so you can, many things can approach there. Of course, if you try to enhance the field on some larger object, this will not work because the near field is really a few nanometers, up to 5 nanometers roughly. So if you have a larger particle of something like 10 or 20 nanometers, only part of the particle will fill the near field. But even large molecules can, in principle, come and attach to the gold. And if you think of, for example, dipole antennas, which are formed of 2 particles, then you have a hard time fitting the molecule in a small gap. Right? It will be difficult to put a big molecule in a small gap without denaturating it or without damaging it. And this is something that you can bypass by using this very open structure of the rod. So those are maybe the most important properties that we like of these gold nanorods. Right, so let's see some of their properties. Photoluminescence, that's a recent work by Achilles Caratino. That's Achilles, so he was promoted now 2 years ago and has started his own company in Holland, doing software and also plasmonic temperature sensing. So what Achilles has found has been working on this photoluminescence. So what you see here is a number of gold nanorods with their scattering spectra, white light scattering in blue, and on top of each of these blue spectra, the green spectra corresponding to photoluminescence. And as you see immediately, this photoluminescence spectra, photoluminescence in my world is just excitation of the gold nanorod with a given wavelength, in this case 532 or 514 or 488, typical laser line. And you look at which wavelengths are emitted by the gold particle. And you see that the spectrum is very similar to the scattering spectrum. Why? Well, there's no mystery. It's just photoluminescence is also plasmon enhanced, just as the scattering is plasmon enhanced. So the same enhancement factor influences both spectra. And you see that, of course, the 2 spectra are not exactly identical. There is in particular a little shift here. But in roughly, this allows you from the scattering spectra or the luminescence spectra to get the information about the plasmon. And this is, of course, very convenient for us because all our setups are geared for fluorescence or luminescence. So we just need to replace our molecules by gold nanoparticles, and we can just do the same experiments. Whereas the white light scattering requires a different source and different adjustments and different objectives. All right. So that's what you do. So what you can do here, sorry, I have to go back. What you can do here is excitation at 532 here, about here. There is some inertia with yes, 532 is about here. And but you can also excite the luminescence with a laser inside the plasmon band. And that's what Achilles has been doing here. So the laser is 633, the helium neon laser, and we excite here. And of course, there are filters to cut the photoluminescence around the laser. The laser light is much more intense than photoluminescence. And what you see is there is, of course, red-shifted luminescence. That's the Stokes shifted luminescence. That's the one you expect. But in addition, you see that there is anti-Stokes luminescence on the blue side. And why is that? Of course, there is always anti-Stokes, but the anti-Stokes luminescence is made visible here and is actually stronger than the Stokes luminescence because of plasmon enhancement. So we took here a nanorod which absorbs just at 600, and our laser is in the red wing of this plasmon resonance. That means that the enhancement is mostly active on the blue side of the line. And that means that enhances the anti-Stokes with respect to the Stokes. And that's very nice because now we have this anti-Stokes luminescence, which, as you imagine, is temperature dependent. If you do at 0 temperature, you send a photon with h bar omega. You know that you can only leave energy in the material. We come out with a photon omega prime, which has to be less than omega at 0 temperature, right? But at room temperature, it's possible to go out with more energy. That's anti-Stokes. And of course, this tail here, or this wing of decay of the line, tells you something about the temperature of the particle. Right? So what you can do with this is either measure the temperature of the particle when you need to know it. Think of, for example, of the photothermal therapy in which you have cancer cells which have taken up some gold nanoparticles, and now you want to heat them and kill these cancer cells, but without damaging too much the healthy cells around them. And the big difficulty in this therapy is to know how much energy or how much power you need to use to fry the cancer cells and not the healthy cells. If you are able to measure the actual temperature of the heating particles independently from other measurements, you know up to which temperature you can go to kill the cancer cells and not damage the healthy cells. And this could be, so of course this is not a demonstration, a proof of concept of this idea, but this is a way you can easily, without two different sensors, with the same particles, heat and at the same time measure temperature and know that you are not heating too hard. Right, let's move to the next one. Yeah, so this is just a demonstration that this really works. So you can measure either the temperature while you are heating, but by extrapolating to zero heating power, of course, you need some power to measure, because without power, there is no photoluminescence, right? So you need to extrapolate to really low powers, and by extrapolating, you get room temperature. Yeah? So you can easily measure absolute temperature, even though you are not heating too much with the particle. You need a bit of light, of course, to see the anti-Stokes photoluminescence. All right, so this is another experiment done several years back by Peter Zijlstra with the help of Pedro Paulo. Pedro is in the audience. Peter is now assistant professor, or associate professor, sorry, I should say, in Eindhoven Technology University in the Netherlands, and he's continuing these experiments with nanorods. And Pedro has done these simulations to help us understand what kind of signals we obtained. So the idea is just to use, again, the plasmon, but this time to detect a change of index of refraction around the particle. So what is going on here? We have functionalized the surface of the gold nanorod, so it's here, the surface of the gold nanorod with biotin conjugates, and then streptavidin molecules, proteins, will come and bind to this biotin conjugate and change the index of refraction in the vicinity of the tip of the rod. If you change the index of refraction, you bring charges, polarizable entities, and these charges will modify the spring constant of the plasmon. Therefore, the plasmon will feel that and shift a little bit, ever so little, and we can measure that. So it's shown here. So when you do nothing, when there is no streptavidin in the solution, nothing really happens. You have this green trace. At low concentration, you see some occasional events. That's a particularly large one, where the particle, the molecule attached to the tip of the particle. And if you increase the concentration, you see more and more of these events happening, adding as a function of time. So this is a sensor, if you like, or sort of sensing experiment in which you see the landing of single molecules on the surface of the rod one at a time. So this was done in that time with photothermal detection. We are measuring the absorption of the nanorod. Nowadays, Peter is doing the same experiments by looking at scattering. You can also measure alternatively the scattering in white light or with laser light. And every time you see scattering change, this tells you one molecule is attaching to the tip of the particle and shifting the plasma. Okay, so now I'm going to talk about fluorescence enhancement. And so we had this very, we had already previous experiments with molecules that do not fluoresce very well. And so, that's one of the big issues in single molecule fluorescence, that in order to have good signals, you need a molecule with a high fluorescence quantum yield. And there are not, of course, that's what biologists use for labeling proteins and different structures in cells. You use a rhodamine dye or these atto dyes of the same family. So you use different kinds of dyes that have a very high quantum yield in order to make things visible by fluorescence. But of course, it's only a very small selective class of molecules that have high fluorescence quantum yield. There are only very few molecules. So it would be nice, of course, to generalize single molecules fluorescence to molecules that absorb light. Of course, you still need interaction with light in this fluorescence enhancement experiment, but with molecules that do not have a high quantum yield. And one of them is crystal violets. We have started with that one. But by discussing with colleagues, with Robert Pinsu from Cachan in France, he told us, well, you should try with methylene blue because it's a nice redox indicator. And we're interested in redox sensing in cells and other media. So we thought, why not methylene blue? And this methylene blue is a nice molecule. So I brought a demonstration experiment with me here, which was difficult to take in a plane. And I think the chemists among you will recognize this experiment easily. So I have a bottle here which is basically transparent. I'm going to shake it. So this takes a few seconds. And you see the color has changed very clearly, right? So if I shake more, it becomes dark blue. So what's happening here is that I've put some glucose in the solution. Glucose is a reducing agent, and there is oxygen in the top. The oxygen wants to reduce, to oxidize the glucose, but it takes some time. So you need to dissolve first the oxygen in the solution, and then the reaction has to take place, so it takes several seconds. So what we were doing here is just dissolving oxygen in the solution, which makes the oxidation, and this is what happens there. You can see here, this is the reduced form. Here it actually has his protonate, has a hydrogen here on the nitrogen. This breaks the conjugation, so this is colorless, does not absorb, does not fluoresce, invisible at least. And when you oxidize, you remove this hydrogen, and you get this conjugated form of methylene, which is blue, but does not fluoresce very well. The quantum Hill fluorescence is a few %, so actually this is not enough to see single molecules under normal conditions. You have to do something extra. So the thing was to use a single gold nanorod to enhance the fluorescence, and this was done by these 3 people. So Wei Chun is now, was a PhD student, he's now postdoc in Karlsruhe with Uli Nienhaus. Biswajit Pradhan is postdoc in the group of Kesdecker in Delft. And Martin Calderola was postdoc, and he's now again postdoc with Kopius Kuipers, also in Delft. So 2 of these people went to Delft. And they are continuing doing optical experiments. And what they did is conjugate this methylene blue molecule. So this is something you can have for cells, actually. You can have this covalent bonding of methylene blue to convenient functionalized molecules. You can attach this to a glass surface and put this in a rod. So those were heroic experiments because at that time we did some progress since then, and we can do that much better with DNA conjugation. But at that time it was really a nanorod on the surface, a low concentration of these conjugated molecules on the surface, and then you have to really patiently, it was really the patience of Wei Chun Jiang which made this possible. You really have to look at many nanorods to find one and a single one of molecules in the near field of the nanorod. So the probability of finding a good nanorod and a good molecule is something like less than 1%. So it's really, you need a lot of time and patience to find it. But if you do that, you can do that. And what you will find, that the Anselmo mentioned, what you will find is actually essentially a trace like this, where you see here. Now, of course, it's not very convenient in our experiment to open and put some oxygen and remove oxygen. This is too time-consuming. So what we do instead of that, we just control electrochemically the potential. So we make the environment oxidant or reductant according to the potential. So we just apply a voltage, and in this way you can tune. So by tuning the voltage, we can change the midpoint potential. We can not the midpoint potential. We can change the equilibration between the oxidized and the reduced forms. And what you see here, if you keep the voltage constant and for 3 different values, come on, yeah, you can see for these 3 different values of voltage, the on-off. So the molecule is now switching between oxidized and reduced, oxidized and reduced. And this is doing, of course, it's doing this automatically. You don't do anything there. You just have to record the statistics. You measure these long traces, and then you do statistics of the time when the molecule is oxidized and reduced. And by measuring the ratio of reduced and so you have the midpoint potential of your reaction. And what you see here in this plot is a few examples, because I told you the experiments were so lengthy and difficult. It's only very statistic with a few molecules. Nowadays we could do better. Which show you that different molecules have actually different midpoint potentials. They react to the voltage in different ways. Why is that? The molecules are identical, of course, but what is different is that each molecule has a different environment on the surface. There are different charges. The ions in the glass or the impurities attached there will create a different local potential, and of course it will shift the midpoint potential, the equilibration between reduced and oxidation, different depending on the molecules. That's what we see here. All right, so more recently we looked at this two-photon excitation. That's another question that we had. Of course, it's a potentially very attractive experiment to do, because you realize, like, for example, in surface-enhanced Raman scattering, you can enhance Raman scattering in this case because of you enhance the field that comes in, and you also enhance the field that comes out. So there is this factor of enhancement which comes twice. So you enhance by field squared, the factor enhancement squared because of the incoming field, and you enhance the second time upon emission by the square of the, so it's E enhancement factor power 4. And so we thought, yeah, in fluorescence, usually we don't enhance so much the excitation because it's usually out of the plasmon, and we essentially enhance the emission. So that's what we did in the previous experiment. But what if we could enhance, for example, the excitation factor twice? And of course, if you go with two-photon excitation, you have your effect, your excitation probability is second order in field, right? So if you go look at intensity, it's already fourth power in field. So you can also have very high enhancement in cells. It can go up to 10 to the 12 or so. So why not try to get very high enhancement, not in nanorods, of course. It's 10 to the 12 in small gaps. So what if we could try with gold nanorods to enhance two-photon process, two-photon excitation, and try to observe that? So we can do that. So the idea of the experiment is shown here. It's very simple. So with one photon, you have the excitation probability is proportional to intensity. If you go with two photons, this will be proportional to the square of intensity. So we try to enhance this step here twice. So we need a nanorod that is resonant, a plasmon which is resonant with the, let's say, the fundamental, not the overtone or the second harmonic of the frequency, but with the fundamental frequency of the laser that pumps two-photon excitation. All right, so it turns out that with single molecules, the experiment is very difficult, actually. We still hope to do it in the next months or years, but it's quite difficult. And the reason of that is that although the enhancement factor is very large indeed, the process itself, to begin with, is very weak. So the product of these two things is actually barely observable. So we decided, let's try to have a demonstration. That was, again, Wei Chun's idea. Let's try to do a demonstration experiment with something which has a much larger cross-section of two-photon absorption than a single molecule, a quantum dot. And this is what is done here. So you see a quantum dot here, which is properly conjugated. And this quantum is going to stick transiently to the surface, and we're going to try and see this two-photon excitation. So this is the idea of the experiment. So the nanorods come here, they stick either to the rod or to the surface, and we try to see transient signals coming from this sticking. And this works with nanorods because they are so bright. So you see here a trace as a function of time, where you see here for this plasmon, for example, in which the laser at 770 was really resonant with the plasmon. You see very bright two-photon signal traces, where the different intervals are due to one quantum dot coming, landing on the surface, emitting photons, and detaching. So this is not bleaching, it's really detaching. This we know. And this is a different plasmon. If you are not as well centered on the plasmon resonance, it's a bit on the wing. You see that the bursts are much weaker, about a factor 10 weaker. So this works. We can do that, and we can also do simulations and check that this is indeed what we expect. So this simulation. The problem with the dot is a bit more complicated than the molecule. In molecule, you have an excited state and one lifetime. It's very simple. In quantum dots, it's more complicated. You have several states, and the lifetime is actually a composition of different states with different lifetimes. And we don't have for every single quantum dot the exact value of all these lifetimes. So you have to do simulations in two different extreme cases. This is shown here. So this is the case where the quantum yield is the same for all the states. And here is the case where the quantum yields are changing for the states. Only the oscillator strengths are known. So these are the two extremes. And so the measurements are actually, probably they are not the same for all quantum dots. What you see is that the measurements are in between. They lie in between. All right, so this is working. We're trying to continue this in the future, but with molecules it's much more difficult. I think I have still 5 minutes to go. Is that correct? Yep. So in the last 5 minutes, I would like to tell you briefly about plasmonic nanobubbles, something which is not at all, or not yet related to single molecules at all, but single gold nanoparticles. So again, what we are going to do here is derived from our work on photothermal microscopy, in which we use two lasers, one to heat, the other one to detect the effect of heating. So if we heat too much, then you expect to see boiling of the liquid in which the particle is. In this case, we work in either water or light gasoline, pentane liquid to see the boiling. And the experiment is shown here. So basically, we have two lasers. One is here to heat, to change the temperature of the gold nanoparticle, which will absorb. This is not a nanorod, just a sphere. Yeah, something that I should have mentioned maybe is that gold nanorods are very nice, but they have one disadvantage compared to spheres, namely that they reshape very easily. So if the temperature of the rod becomes too hot, too high, the surface atoms start to move, and the shape of the rod is changing with time. So you start with a given plasmon, and if you heat too much, the plasmon will start to shift. And if you do it too much, it will become spherical even, and then plasma completely shifted to the grid. So that's why we have to go with spheres, because we want to heat a lot, and spheres are not readily reshaped like rods. Right, so now there will be this change of temperature, and when the temperature is changed, the index of refraction will also change, and a second beam at a different frequency, for example, 800 nanometer, will be scattered in a slightly different way. So our signal here will be changed by the temperature change. So this is a way in which you also can measure the temperature in a much more intricate way, indirect way, than the Anti-Stokes Photoluminescence I discussed before. But of course, it's very sensitive to look at a bubble, because a bubble is a huge perturbation in refractive index. If you just heat a little bit, you modify by maybe 1 or 2 digits the index of refraction. If you change from liquid to steam, to vapor, the change of index of refraction is from 1.3 or 1.4 to 1. Yeah? So it's a huge effect on the plasmon and on the scattering. So the experiments, original experiments have been done by Lei. So Lei came back to China, and then actually has been first in Zurich with Madhavi Krishnan, who is also present here. Then he went back to China, and then now I think he's in Bordeaux with my colleague Bohem Lunis doing spectroscopy back again. And the experiments have been continued by Thomas Julans, who is going to defend his thesis hopefully this year. So this is basically what we try to do. We try to boil, and we try to keep a vapor shell around the particle. As you will see, this is the difficult part. So what do you expect for a liquid boiling in such a small vessel, if you like, right? If you boil normally water, for example, at room pressure, you create big bubble, and this happens at exactly 100 degrees Celsius at atmospheric pressure, per definition of the Celsius scale. Right? But if you do the same experiment now around the gold nanoparticle, the first bubble that you have to create is shown here, is quite small. It's nano-sized. It's a sub-micron size. It's typically a few tens of nanometers in radius. And that means this very small bubble has a very huge internal pressure. That's a Laplace or Laplace-Young pressure, which is due to surface tension. And because we are still far from the critical point, this surface tension is pretty high. So this pressure, this added pressure, twice the surface tension divided by the radius, because the radius is so small, this pressure is typically several atmospheres, 10, 20 atmospheres. So this means that it's like in a pressure cooker. So you have to heat much more than you would have to heat if it would be a macroscopic object. So this boiling requires more power than and you can measure that. This is a simulation, but you see that as soon as you form the bubble, what happens is that, of course, the bubble is made out of steam, a very bad heat conductor. So there is a jump in temperature. And this explains to you why you cannot, we don't like to work with water, because if we want to boil the water, we have to go to temperature, which are typically, okay, in Kelvin, 500 or more Kelvin, and then gold really starts to become soft. Even the nanospheres start to change shape. We don't keep the particles. So that's why we decided to do this in pentane, in this light alkane liquid, which boils at about 50 Celsius. So it's much lower temperature. Gold is completely stable. So we can do the experiment. And this is what you see here. So if we do this experiment in photothermal, you see something sudden happening here. So this is this boiling transition as we expect. But actually, when we looked at the time trace, what you see is this. So the time trace, while we're heating continuously, is very noisy. So this time trace is shown here. This is a scale in microseconds, 100 microseconds. If you zoom in, you see that there is a burst an explosion actually, every microsecond or half a microsecond. So very high rate bursts which are caused by instabilities. So it's just the same instability you can hear when you boil water for your tea. You hear the bubbles doing ding, 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 right? So this is basically the same phenomenon, but because our pan is so much smaller, typically sub-microns, the times are also much shorter. So the time of the explosion, time of the bubble is typically a few tenths of nanoseconds, and the duration between explosions is typically 500 nanoseconds or half a microsecond. I should stress that this regime is very hard to reach. It's an unstable regime at the limit where you have this simply no boiling at all, and chaotic boiling where you have a lot of convection and instabilities due to transport at a large case. But if you choose the right heating power, you can really reach this regime. So this may be interesting, for example, to release sound waves. So these explosions are extremely brief and energetic effects that release a lot of energy in the environment under the form of not only of heat, but also of mechanical acoustic waves, which can have mechanical effects. Think of cells, for example, in which you can destroy some cells not due to the laser pulse. This is, again, CW, laser power. But spontaneously, the system becomes unstable and gives rise spontaneously to these explosive events. All right, so I think that's, I have to stop now because the time is up. And this is a slide just to remind you of the main subjects. And I stop that now, and thank you for your attention.
Thank you, Michel, for exciting, excellent talk. So, questions from the audience? Yes?
Thank you very much for the excellent talk. Yep. Thank you, Michel, for the excellent talk. And I have one question. What do you mean when you say that quantum dots has a lot of states with different lifetimes? Is it traps or defect states or?
Yeah, so that's complicated matter. You know, I worked on quantum dots many years ago, then I stopped, so I didn't follow the recent literature. But when you look at the lifetime histogram, so you look at the photon distribution, photon delay distributions that you measure in a lifetime experiment, right? A single quantum dot, you find not a single exponential, but a distribution of exponentials, which is at least 2 or 3 exponentials, more than 2. I mean, at least 3 exponentials, or maybe continuous. And of course, these different decays correspond presumably to different states that have different quantum yields. And of course, if you want to model the enhancement, you need to look at the enhancement of the emission for all these different states. And you don't know. I mean, of course, you know the lifetimes because you can measure the decay. At least on the ensemble, it's easy to measure the decay, but you don't know this distribution and all the factors, the quantum yields and the properties for every individual quantum dot that you are measuring. So there is some adjustable parameters in this calculation, and you make assumptions either of all the states of the same quantum efficiency of emission of 1. And that was one of the curves. Or you suppose the other assumption was that really the lifetime is due to, I mean, shorter lifetime corresponds to a lower quantum yield. And the oscillator strength, if you like, is just the same for all the states. So the same level absorbing, but with different radiative quantum.
Okay, I see.
And those are the two extremes. And the simulation, and the results that we measure are just between these two simulations. So, which means that very probably we don't have the right parameters, but we would be able to simulate our results by adding, more adjustable parameters that we don't know.
Okay, thank you.
Thank you. Yes, Warwick.
Oh, hi. Thanks for the talk that you just given me. It's been really interesting. Just a quick question for you. You've mentioned during your talk that you've actually held the potential using the potential state. Did you hold the voltage at constant voltage? Because we were talking about oxidation reduction of your device. Did you just hold it at 1 voltage, or did you vary between oxidation like negative and positive, or was it just constant?
Yeah, so this is a question about the electrochemical cell that we used. So, of course, we can do this experiment in different ways. We are not electrochemists, so we discuss with colleagues. And so what we do in this experiment is very simple. We minimize the volume of our cells so that we don't have a long diffusion time. So typically, we waited a minute to have a stabilization. And all the measurements I showed you were done at a fixed voltage, and you measure statistics of these on-off times. And then you change the voltage, you wait 1 minute, and you measure again, change the voltage, measure again. And you do that for every single molecule. The long part of the experiment is to find the single molecule close to the nanorod. Once you have done that, the molecule is stable for at least several minutes, especially in the dark when you don't measure. So you have time to vary the voltage, and for each voltage to acquire a trace.
So you varied your voltage just positive. It wasn't like a negative voltage or a positive. It was just positive voltage.
I can go back to my slides to show you. Yeah, so that's here. So that's a sketch of. So that's the ensemble measurement. This is done, of course, with an ensemble of molecules on a long time scale. And what you see here is just the fluorescence intensity. So here we don't have the statistics of single molecules, just the average, right? So the average goes up in a normal way. That's a nonce equation fit. And if you look at this, what you see is that here for each of these molecules, this is one experiment. This was very, as I said, very lengthy measurements. So for this molecule, you stabilize the voltage at these values. You see that these voltages, we chose this voltage, and we measure all the molecules at this particular voltage, for example, 80 millivolts, right? But of course on different runs, so 80 and 100. Yeah. And so it was measured in this window between 0 and 140. Now don't ask me whether this respects to the standard calorimetric electrode or hadron electrode, I don't remember. But this is exactly the voltage you need to get this equilibrium in methylene blue.
Thanks a lot.
Okay, maybe one, do we have time for one more quick question, a very short question, last one?
I got the microphone first, I'm sorry.
Good.
Yeah, go ahead, yes, please.
Thanks for this inspiring talk. My question is, how did you avoid quenching of the quantum dots by the gold nanorods, but you observed this enhancement?
All right. So the question is about what about quenching of luminescence of the quantum dot by the rod? So first of all, while the quantum dot is not exactly in contact with the gold, right? There is this functionalization layer that is schematized here. Sorry, it's just there. So this is a few nanometers. It already creates a distance between the rod and the gold of the material and the core of the quantum dot, which is the emitting part. And secondly, of course, I do not guarantee that there is no quenching. There may be already a lot of quenching. And actually, in the calculation, the quenching is also included. And the distance has been taken reasonably to correspond to the structure. So you can calculate it. I mean, it doesn't prevent you, the quenching may be there, but that doesn't prevent you from seeing the emission. So, I mean, some degree of quenching is completely tolerable as long as you have enough photons coming out, right? So definitely there should be some quenching. I cannot tell you from memory how much it was, but it's definitely more than 10 or 20%. But definitely not 90% or more.